Okay, all right. Um, okay, let's look at the last topic, yeah, which is chapter 10 actually, not chapter 9. This should be chapter 10. All right. Which is actually on the multiple linear regression model. Okay. Um, the multiple linear regression model, yeah, or the MLR, is just quite similar to the simple regression model, except that there's some things extra basically for the MLR. The technique is still the same. Yeah, we are still going to use the least square methods. Yeah, just like the simple. And the MLR is actually an extension of the simple linear regression. Right, let's look at what is MLR all about. Yeah, okay. So in the simple regression in the last class, all right. So what we do is we have actually finding the equation between a single independent variable, that means one x, all right, with one y. X going to y. Okay, this is what we did. Now in the multiple, what we have is we now have more than one x. Yeah, so that means to say that we now have multiple independent variables. That means there's a lot of the x, okay, relating to y. So the whole thing is we just want to see, all right, how does this independent variable x1, x2, right up to xk, all right, be affecting the value of the y. That means we now have a few more independent variables. Yeah? So for example, if I say you're looking at yield, all right, it could now be y is your yield. Let's say this is your yield. Okay, so your x1 can be temperature, x2 can be pressure, all right, xk on can be volume, so on. Yeah, all right, so basically we just want to see how does this x1, x2, they are independent, meaning to say that they do not depend on each other. All right, so they are independent, and then trying to see how does each of these variable be affecting the value of the y. Yeah? So that's why we say that it is multiple, because we consider x1, x2 right up to xk. Okay. So it's still a simple linear regression. We have a straight line. So in the case of a multiple regression model, so we will have a plane, like if we have two independent variable x1 and x2, yeah, but it can extend beyond x1 and x2. Yeah, it does not matter, but the equation itself is just a linear equation. Yeah, that's why we call it as linear regression. Okay, in the simple regression model, you want to find this. Okay, this is what we want to find in the simple linear regression model by minimizing the square of the error. Yeah, minimizing the SSE. So in the multiple, you now extend this equation to make it a bit more, because you now have x1, x2, x3, x4, right up to xk. So this equation will now change. So how will it change? It will change in this manner. So it's just an extension of the simple linear model. Okay, but it is used to model more than one independent variable. So you have a data set that look like this. So just now if I say the yield is, let's say, 20 kg, pressure is, let's say, 100 bar, temperature is 20, and then let's say the volume is 10 ml or something like that, yeah, or 10 liters, okay, or 10 tons or whatever. So this is what we have. Yeah? So we're going to see how does each of these be able to come up with an equation of y is equal to beta naught plus beta 1 xij, yeah, okay, plus beta 2 xi2 plus beta 3 xik and whatnot, yeah. Okay, so basically we're just trying to find still the same thing, what is beta naught, what is beta 1, what is beta 2, okay, and so on up to beta k. Now the fundamental is still the least square method. That means we are still going to use the least square method. That means we are going to minimize error, okay, and then still trying to find okay, beta naught, okay, and the other beta i's. Okay, yeah. So this is what we are trying to do. Okay, so still using that. Now, because it has now become quite complex, yeah, because it depends on how many x you have. So if you have 10, then your coefficient will be beta naught plus beta 1x1 plus beta 2x2 plus beta 3x3 plus beta 4x4 and so on up to beta 10x10. So it's going to be quite a lot for you to actually evaluate the value of the model parameters. So what we do is, okay, um, how do we actually evaluate that? So what we do is we basically run this on the statistical software, yeah, to handle all the computations. If not, in order to find all the beta, you will need to use your what do you call that, computational methods, yeah, the Gauss elimination, the matrices, you got to solve the matrix, yeah, in order to get the values of the beta naught, beta 1, right up to beta I or beta K, yeah. So because of that, we basically use the printout, yeah, the Excel, okay, or the Minitab or whatever, or MATLAB for whatever the software that we're going to use, basically to find the value of the beta naught, beta 1 up to beta K. All right, so this one we don't normally do it manually. Okay, but bear in mind, okay, when we run the ANOVA, okay, sorry, when we run the statistical software, all right, we're going to end up with the ANOVA, also the R squared values and so on and so forth. Yeah, so basically what we need to do now is, okay, we run it on the Excel, for example, get out the whatever the printout is, and we just need to do the interpretation. Okay, so this is what we do. All right, so we run on the statistical software. Okay, Excel or what, yeah, okay, then get the printout, get the output, okay, and interpret. Okay. So interpretation is still the same. Find the coefficients, okay, run the assessment, okay, the 4 assessment that we did in the last lecture, yeah, for the simple linear regression, and then only we use the model. Okay. Yeah, so this is what we do. So we're gonna run it, get the output, okay, get all the coefficients, the beta naught, beta 1, beta 2, that depends on how many beta that you have, okay, and then run the 4 assessment. Remember the standard error, the R squared, the t-test, and the ANOVA. And finally, if everything is good, like what we did for the simple regression model, then we will say that this model is actually a good model. Okay, so one thing that you need to note is, in the case of the multiple, the ANOVA will be used to test whether the regression is significant or not. Okay, and the t-test be used for individual coefficient. Now, why I say it's individual is the fact that you may have 10 independent variables, but at the end of the day, what matters is only 5. So you can eliminate the other 5 because it does not contribute anything to the value of the y that we are looking at. Yeah. So how do we determine that? We determine that by using the t-test. Okay. So we look at it a bit more. Yeah. Okay, so this is an example of the MLR. Yeah. Okay, so why I say this is an example of the MLR, because of the fact that you now have 2 variables, wire length and the die height, okay, which is x1 and x2. So now it is multiple because you have more than one x. So what you're trying to do is you're trying to find the relationship between the pull strength, the wire length, and the die height. So that's what you want to find. That means this is your y, this is your x1, this is your x2, and altogether you have 25 number of observations. Okay, so this is for observation number 1, observation number 2, observation number 3, and so on and so forth. So this is observation number 5. So that means when the pull strength is 21.15, your wire length is 5, and your die height is actually 400. Okay, so this is taken from some experiment. Yeah. Okay, so how do we find this relationship? All right, so the best thing to do is basically to run it on the Excel or on any statistical software. Okay, so this is what we are trying to find. Okay, that means this is the value of the beta naught, beta 1, beta 2, beta 3, beta k. This is what we are trying to do. Okay. Okay, so in yeah, all right. So using the least square method, all right. So what I do is this is done using some statistical software. So at the end of the day, we end up with beta not having a value of 0.568. Beta 1 gives you a value of 2.706, and beta 2 gives you a value of 2.051. So this is the equation. All right. So the equation that relate the y just now, all right, the pull strength, yeah, with the die height and the other variable, right? So this is what we want to find. So notice that it is a linear because the x1 is raised to the power of 1 and the x2 is raised to the power of 2. Okay, so this is our objective. To find this equation. Okay, and then once we find this equation, we will have to do the assessment of the model. Yeah, so this is what the multiple regression is basically all about. Yeah, so it's just trying to find the equation, just like the simple, but the difference is on the fundamental that we now have a more independent variable. Yeah. Okay, so what we normally do is we run it, yeah, and we always look at the ANOVA, yeah. Okay, so how do we test for the significance of regression, yeah, for the ANOVA? All right, so this is the difference, yeah, between the simple and the multiple. For the simple, all right, because we just have y hat is equal to beta naught plus beta 1 x. So our interest is just to look at the slope. Okay. Now, because we now have a lot of beta, right, just like the one-way ANOVA, remember, where we have more than 2 means, yeah, so it's basically the same thing. we now say that if the slope is all equal to 0, then y will not be depending on any one of the independent variable. So we put the hypothesis of h naught, all the slopes is equal to 0, okay, or beta 1, beta 2 is all equal to 0, and at least one of them is not equal to 0. Yeah, that means if any one of these is not equal to 0, then we say that there is a linear relationship. The test statistics is still the same, no difference. Okay, still using the F statistics. Okay, so the F for the mean square error, MSR, mean square of the regression, we found that by using SSR divided by 1, because we now have only one independent variable. And MSE is found by SSE divided by n minus 2. All right, so here, in this case, we have to change a little bit because we now have more than one, yeah? So the ANOVA will be still division of SSR divided by how many independent variables we have. Let's say we have 3, then this will be divided by 3. SSE over n minus p, which is again p is equal to k plus 1. And finally, this is the one that we are interested to look at, and then we compare that with the table. All right, so this is the same. Yeah, you have done this for the simple. It's just an extension to the multiple. The only difference is in terms of the hypothesis test. Yeah, so I think this is just to put writing the hypothesis. Yeah, the rest will all come naturally when you do the ANOVA. Okay, so again, yeah, the ANOVA is put in the form of a table. So K means the number of independent variable, n minus 1, the number of observation, okay, and minus K plus 1. Okay, this is sometimes written as P, and then what is our interest is just the F statistics. So this is the F that we are going to compare with the table, right? So this is what we have, yeah. Okay, remember this ANOVA is just to say whether you can fit a linear equation or not. Okay, it doesn't tell you which of the X is important in that relationship. Okay, in order to look at which of the X is important, so what we do is we need to put in the individual coefficient, yeah. And the test statistics is the same, just like the simple regression. We take whatever the value of the beta hat, okay, minus, and we always put this as 0. Yeah, we assume this to be equal to 0 because of the fact that if the slope is 0, that the value of that particular x, yeah, divide by the standard error. But our t-test is now t alpha over 2 n minus p. P here will be k plus 1, yeah, depending on the value of the number of the independent variables that you have, yeah. So this is to do for individual. Okay, the ANOVA is for in total, yeah. This is what we do. Okay, so let's go back to this. All right, the pull strength, the wire length, and the die height. Okay, die height. Yeah. Okay. All right. So how do we get what do we get when we run? Okay. This is what we get. Okay. So this is the multiple regression output. Yeah, based on the data that we had. Okay. Um, this is run, I think, on the many tab, if not mistaken, yeah. Okay, but what is our interest is basically to just pick up what is important in this output. Okay, what is important? The first one is to find the value of the beta naught, the beta 1 hat, and the beta 2 hat. Why I say this beta 2 hat? Because you now have two variables, yeah, x1, x2. So that's why if we look at this, again, we always go to this column. Right, this tells you your constant value, the length, and the height. So these are the one that is of interest to you. All right. Okay, so what's the beta naught? Look at the coefficient column. So the beta naught will correspond with the constant. So that gives you 2.264. What is your beta 1, which is the length? Beta 1 hat gives you 2.74427. And the height gives you a value of 0.012528. So that's why this equation is there. The strength is equal to 2.26 plus 2.74 of the length plus 0.0125 of the height. Okay, so this is equation that we want. Okay, so first of all, you get the equation. So from the output, okay, number one, get the equation first. Okay, that means reading all the coefficient. Okay, next one, once you get the equation, what you need to do now is to run the 4 types of assessment. Yeah, okay. So now once it's done, so we do the 4 assessment. Okay, so the first one is the standard error of the equation. Yeah, okay. That means what is a standard error? That's a sigma hat. Okay. So what is it? So it's a value of this value. Okay. So this gives you a standard error of 2.288. Yeah. So that means the data will deviate about 2.288. Yeah. All right. Okay. So you need to decide whether this is small or big. Okay. Then the next one, we look at the R squared. Okay. So once we are okay with that, the next one is we look at the R squared. Squared, we want a value that's big. Okay. So we get a value of 98.1. So this is a good fitting, or almost 98%. Yeah, is accounted by the 2 variables x1 and x2, the length and the height. So this is okay. All right. Okay. Next one, we look at the t-test. Okay. In the t-test, okay. So in the t-test, all right, you need to look individually. Yeah? That means you need to look at, first, let's look at the length. All right. So what's the t statistics? So t statistics is basically the coefficient 2.74427 divided by the standard error. Yeah. Okay. This is the formula. Yeah. This formula. Beta j hat minus beta j, all right, over the standard error. All right, so we assume that our beta 1 is equal to 0. All right, so 2.74427 minus 0 divided by 0.09352, so we get a value of 29.34. Okay, this is the value of the first test statistics. Okay, so now we need to see whether it is okay or not. Yeah. All right. So if you look at this, this is the p-value. Okay. All right. The p-value gives a value of 0. Yeah. So 0 means less than 0.005. So that means you will reject the H naught. So meaning to say that the length is significant. All right. So look at the p-value. Okay. Um, since it is about 0, and less than 0.05. Okay, So we say that X1 is significant. Okay, right? Now let's look at the other one. All right, the other one is the height. Okay, so we have again 0.01258 divided by 0.02798. So we get 4.48. Okay, so 4.48. All right, we want to see whether it's significant or not. All right, in case here, because we've got the p-value, so the p-value is actually 0. So we say that, yep, all right, the value of the height is also significant. Yeah, so same argument with x1. So we say that x2 is significant. That means x1 and x2 is important in this relationship. Okay, let's say, for example, let's say if this p-value is equal to, let's say, 0.06. So 0.06 greater than 0.05. So we fail to reject the H naught. So for that reason, the height is actually not significant. All right. So that means if you have 10 coefficients, so you have to do for each individual one, all right, to decide which is important and which is not important in that particular equation. Okay. Then we go look at the ANOVA. Right, so this is already calculated for you. Yeah. So 24 because you have 25 observation. Why I have 2? Because I only have the length and the height. So there's only 2 variables. Uh, 22, 2 plus 22 gives me 24. The sum of squares is calculated, is calculated using some formula. You just cannot calculate the sum of squares using the formula that you are used to. Yeah, all right, okay. So the error, all right, okay, the error can be calculated based on that, yeah. And then we have this value, and then we calculate the mean square, right? Then we get what's the value of the f, yeah. So notice that f value here is 572.17, which is very large, and of course the p value will be about 0. So we say that the regression is significant. From the ANOVA. Okay? So from the ANOVA, we say that the regression is significant. So then if this is fine, we are okay with that, then only what we do is we will just go on to do the prediction. So after that, so if all is okay, okay, then we can use this equation to make prediction. Okay. Yeah. So this is what we basically have. So it's kind of like the simple, except that now you just have a bit more, yeah, in order for you to see. You have a bit more variables here. The ANOVA still remains the same. It's still the regression and the error. Only it does not change anything. It does not increase even when you have more variables. Yeah. The only thing is just this part. It will change a little bit. Okay. Any questions so far? Questions? For now, no. Okay. All right. Okay. So, uh, yeah, this is what we do. Yeah. Okay. Okay, so this is an let's just look at this example. Yeah. All right. So a set of experimental data were made to determine the way of predicting the cooking time at various levels of oven with X1 and the temperature X2. So this is the data that is basically recorded. All right. So you're asked to estimate the multiple linear regression equation from the data and to test whether the regression explained by the model in part 1 is significant at the 0.01 level of significance. Okay, so basically this is what we want to do. Okay, so we are given a set of data. We want to see how we can fit this particular equation, yeah, and then be able to estimate what is the equation and finally run the significance of the equation. So I use it straight away, yeah. Okay, using the I run it on the Minitab. This one is run on the statistical software, the Minitab. Okay, all right. So this is what I basically get, yeah, for the output. Okay, so from here, if I were just to have a look at it, yeah, so I'm going to see that this is my coefficient constant. That means this is my beta naught. So that's why I have 0.568. The width 2.706 multiplied by the width and the temperature, which is 2.051 temperature. This is calculated for me, all right? And also this is calculated for me. And this is the p-value, okay? Right, if you look at this p-value, you notice that the p-value for the constant is actually 0.364, yeah? So if you look at it, it means that the constant is not important here. So meaning to say that there's a possibility that this line will just run through the origin, yeah, the 0.00, because of the fact that the value of the constant is not significant, yeah. But that is not our concern, yeah. Our main concern is to see whether the width and the temperature is important or not, yeah. So if you look at this situation, you notice that this is a value of 0.00 and also this is a value of 0.00. So this gives us something that is significant, yeah. So because it is significant, so we say that the width and the temperature is important in this particular equation. All right. Okay, then we can consider this equation in total. Yeah. All right. So look at this is 0.6334. All right. R squared is very good. 99.9, which is almost 100%. Yeah. Degree of freedom, 2, because two values. Okay. X and width and temperature. Total is 10. All right. So I have 9 and then I calculate the sum of squares. Because it's run on some software, they give the degree of freedom first, yeah, then followed by the sum of squares, yeah. But it's the same. So at the end of the day, this is my F. F is very large, so 13.647. So of course, my p-value will be about 0. So for this fact, okay, I know that this regression equation is actually significant. Okay, so but this is how I will do the interpretation. Okay. Okay, so what is the model that I'm looking at? The model is just this. Y hat is equal to beta naught hat plus beta 1 hat of the width plus beta 2 hat of the temperature. So I get the cooking time to be equals to 0.568 plus 2.706 of the width plus 2.051 of the temperature. Okay. So if I just want to see whether the regression is significant or not, I just run the ANOVA. Okay. So what will be my hypothesis? Basically, because I only have two values, beta 1 and beta 2. So I assume that beta 1 equals to beta 2 equals to 0. Okay, against beta 1 and beta 2 are not both equal to 0. So my test statistics will be the F test. Okay, this is doing it. This is what I will do. I test, yeah. Okay. Right. Then once I got this, okay, so if I do not know the p-value, so what I'll do is, okay, because it tells me that the significance is 0.01, so I read that from the table. Yeah. So alpha 0.01, k is 2. All right. This is always the degree of freedom for the error. So I get a value of 9.55. Yeah. So of course, this value that I get, yeah, is bigger than 9.55. So that means I will reject my H naught. So when I reject my H naught, it means that I can fit a linear model is fitted between Y and at least one of the independent variable in the model. So meaning to say that my model can be Y hat is equal to beta naught hat plus beta 1 hat x1 plus beta 2 hat x1, or it can just be hat equals to beta naught hat plus beta 1 hat x1, or it can be y hat equals to beta naught hat plus beta 2 hat x2. All right, so it can be anyone. That's why I say a linear model is fitted between y and at least one of the independent variable in the model. So this is meaning to say that the regression is actually significant. So the F test does not tell you which of the X is important. The T is the one that tells you which of the X is actually important in that regression analysis. Okay, so this is how I will do the analysis for that. Yeah. Okay, that's it. So this is the your self-assessment one, and yeah, self-assessment two. Yeah, yeah. Okay. So any questions? Let's first. Okay, let's see. Valley have some questions. Okay. Yeah. Yes. For multiple. Yep. Yes. Yeah. We calculate by everything by Excel. Yeah. And then we interpret the result. You know, let me go to a blank slide. Okay. What is important is basically is this. The objective is to find the equation. Plus beta k xk. Okay. So this is what you want to do. To find this equation first. Okay. Right. So how do we do this? we run it on the Excel. Yeah. For the multiple, you have no choice. You have to run it on the Excel. Yeah. Okay. After we have run on the Excel, so what we do is we do the assessment. Okay. So the assessment is of course finding this one, which is a standard error. Okay. And then we find the R squared. Okay. Right. Then we do the normally I look at the ANOVA first. Why? Because the ANOVA tells me whether a linear, whether this equation exists. Exists. Right. Then okay, because this is to say that yes, this line is possible. Yeah, that's why I said to see whether the linear equation exists or not. Then finally, only I will do the t-test. If I do this, if I'm supposed to, how do I do this? Do it properly. Yeah, I mean to show my workings and whatnot. Yeah, I run it first, I print out. So this is what I'll do. Yeah. So the first one, I will get will be the equation. Okay, and then I look at the r squared. I look at the standard error and the r squared. The reason why is because if I get a value of r squared that is small, I mean, meaning to say that getting it less than 0.5, then no point of looking at the rest. Yeah. Okay. Once I'm happy with this, I'm happy with the r squared, then only I look at the ANOVA. All right, ANOVA, I'll put in that manner. Just now beta 1 equals to beta 2 equals to beta 3 up to beta k equals to 0. And at least one of them is not equal to 0. Then I will do it. Okay. I look either at the p-value if it's given, or else I just look at the f. If the f value is very large, in hundreds, it's always p-value will be about 0. So we will reject the h naught. Okay. So then I will say that, yeah, you can fit a straight line. Then only I'll go to do the t-test to see the individual um, individual significance. All right. Because like I said, yeah, sometimes you have 10x. Does not mean that all the 10x, x1, x2, x3, right, to x10 is important. Doesn't mean that, yeah. So it means that or maybe out of the 10, only x1, x2, x3, x4, and x5, x6, let's say, and x9 is important, right? Maybe 7, 8, and 10 is not important in that particular relationship. So we can remove that. Okay, the whole idea is to get the best one, yeah, that basically fit the line, yeah, fit the data that we are actually trying to get that relationship. All right. So if one of these value is not significant, so you may want to just when you collect the data, you may not want to collect that particular value because that value does not contribute anything at all, yeah, to the uh, why that we're actually trying to find out. Okay. So this is basically what I normally do, right? So the objective is just this, running that, okay, and then only doing the t-test for each of the individual to see which of the value of the x is significant or not. That's basically, there's a difference between the simple and the multiple. The simple, because you only got one x, so you have no choice. It will have to be significant, all right, or else you will not get the y is equal to beta naught hat plus beta 1 hat X, yeah, if it's not significant, yeah. But in the case of the multiple, you have more, yeah. And in reality, we always deal with the multiple rather than simple. Okay. So let's have a look at yeah. Can we just run through one of these questions just to make sure that you're okay? Do you still put in the question or you rewrite? Normally we rewrite. Normally we rewrite the equation. Mm, yes. Yeah. Normally that's what we do. Because you may want to put other variables, you know. Yeah, yeah. Normally that's what we do. Okay, let's have a look at this uh self-assessment 2. Okay, yeah. Can we just run through this? Okay, because this is the one that has been the printout is given to you. Okay, right. So let's have a look at this. Let's take about 5 minutes or not 5 minutes, about 10 minutes or so. All right, to do this, then we discuss this equation. Sorry, this self-assessment 2 problem, because this is the easiest, I think, for for now. Okay. All right. So we take about 5 minutes break and then we continue with this. So let's do this. So look look let's look at self-assessment 2. The rest, okay. The rest, are you already? Okay. Okay. The rest, everybody up. We can discuss the how we answer A, B, and C. Okay. All right. Let's look at how do we fill up the missing values. Okay. All right. Let's look at this one. Okay. So what do you get for the value of your T? What's the value of T? Okay, let's fill up row by row, yeah. Okay. T value, okay, for X1. What's the answer? What do you get? What do you get? The T value for X1. Okay, let's see how we get the value, yeah. All right. Okay. How do you get this value here, yeah? All right. So the T value for X1, okay. Yep. So the T value for X1 equals to yep, 0.741, 0.7, yeah, 0.7417 divide by 0.56, sorry, 5768. So you get it to be equal to 1.286, I think so. Okay, so this is how we get the T value for X1. Okay, so what's the P value for X1 here? What's that? What's the P value for X1? Look up the T table. So what do you get? Mm. 0.1. Okay. All right. Anybody with a different answer from Vivian? Anybody else with a different answer from Vivian? Same. Okay. All right. So what's the p value? The p value is actually okay, this is the p value. This is the p value. 0.2 and 0.3 because you forgot to multiply by 2 because this is a two-sided test. So the t-test is a two-sided test. So don't forget. All right. So it should be 2 times of 0.1 multiplied by that. It should be, you all forget to multiply by 2. Okay. That should be the p-value here. Yeah. So don't forget that it's actually what you all did here, but you just need to multiply this by 2. Okay, then you get it. So it's actually 2 times of uh, 0.1 less than the value less than 2 times of 0.15. 0.15. That's why you get it as between 0.2 and 0.3. Okay, right. Next one. What's the coefficient of x2? Cient. Coefficient of x2, what do you get? Come on, guys. Yeah, 9.11. Yeah, I get 9.1138 or 9.114. That's okay. Yeah. Yes, that's the answer. All right. So yes, 9.114. That's okay. Yes. All right. So what's the p-value? P-value for x2? How do you get 0? Huh? How do you get the value of 0? Okay. What's the p-value? Really? Are you sure you get 0? How do you get 0? How do you get 0? At the table, how do you get 0? I get value of less than 0.001. 0.001. So I have. Hmm. That's my p-value. Less than 0.001. Hmm. Did you get that? Search for 13.87. Degree of freedom is oh, too big. So I assume equal to 0. Okay. All right. Okay. All right. Okay. That's fine. All right. So what's the value of the standard error? So what is the value of the standard error? Yes. Okay. What's the value of the standard error? Here. Okay. 0.832. Yep. 0.832. This is the value of the standard error. Okay. Yep, you should get 0.832. Not 0.8165, yeah? It should be 1 minus, sorry. It's actually square root of the SS. It's actually this the square root of this value. Right. Okay. R squared. R squared. Yep, R squared is 88.5%, right? Loss, you better tell me. Okay. Yep, that's right. Okay. Degree of freedom for the regression. Degree of freedom for the error. Yep. Okay. Degree of freedom, yes. 25, yeah. Okay, degree of freedom here is, this is 2. This is 25. Okay. Now, what's the value of the MSE? What is MSE? 0.3, that's correct. 693, yep. And what is F? What is the value of F? Yeah, yes, correct. 96.22. 96.2, yep. Okay. So we get F is equal to 96.2. Okay, so this is how we fill up the table. Okay. Then you can answer what is Y is a dependent variable. Write the regression equation for the output. Okay. Then is the regression equation significant? So part B, you just need to back. So the equation will be equals to part B, yeah. Y hat equals to 3.318 plus point 7417 x1 plus 9.114 9.114 x2. Okay, so this is part B. Yeah, then part C is you do the ANOVA, is get the hypothesis test. Okay, for the using hypothesis test using the ANOVA followed by the t-test. Followed by the t-test. Yeah, so you have the hypothesis test using the ANOVA followed by the t-test because of the fact that one of the t is not one of the value of the x is not significant. Yeah, the x1 is basically not significant because the p-value is between 0.2 and 0.3. Then you rewrite back the equation. Okay. Yes, that's it. So this is for multiple linear regression chapter. Okay, so any questions? So we are done. So we have completed the whole lot. Okay. So chapter 1 is on descriptive statistics. Chapter 2 is on the discrete and continuous. Okay. Then chapter 4 is on the binomial. Chapter 5 is on the normal and the approximation. Chapter 6 is on the sampling distribution. Chapter 7 is hypothesis test for single. Chapter 8 is hypothesis test for two population. Chapter 9 is the simple linear regression. Chapter 10 is the multiple linear regression. And chapter 11 is the one-way ANOVA. So basically, we are done. All right. Next, revision class. All right. So let me know what you want to do. You want to do look back at the self-assessment questions. All right. We discussed that. Or you want to have some questions or whatever, then let me know so that at least I can prepare that. Okay. Then week 12 is your, I think the assignment will be done in class, all right, during the lecture hour. Okay. And then your test 2 will be the following week, week 11 tu tak salah saya. Okay. Next weekend, not this weekend, the other weekend, I think. Yeah. Because this weekend the e-learning is down. Okay. All right. So any questions? Any questions? Please ask. Can we discuss quiz 2 in the next class? Okay. Yep, we can. Yeah, no problem. Yeah, we can do that. Pos mm, you mean for the multiple um for the t-test, okay, if the ANOVA says that it is significant, for the t-test, at least one of the x must be significant. At least for the t-test. It cannot be all, let's say if you have x1 and x2, x3, it cannot be all not significant. It's not possible. If the ANOVA says so, that it is significant, at least one of them must be significant, or else something's not right. Mm. Okay, any other questions? Can you follow so far? Any problems? Okay. Okay. All right. So if you okay. So if you don't have any, yeah, you telling me you have no problem. The rest is just keeping quiet. So whenever you keep quiet, I assume you're okay. All right. Okay. So can you revise chapter 9, 10, and 11? Yeah, 9, 10, 11 is what? Can I show to get the p-value? Okay. Um, okay, I will show you how to get I'll show you how to get this in the next class, Valley, because my screen is completely dark. All right. So if I share my screen now, you're gonna see a dark screen at the moment. Okay. All right. Yeah. So my PC is not right today. Okay. So we will run through this again so that I will show you how to get the p-value in the next class. Just remind me. Okay. Something's not right with my PC this morning. It's like half dark and half there, half sometimes not there. Yeah. Okay. But what you need to do is you just, okay, roughly, okay, this is how you find the p-value. You look at this value, 13.87. Okay. Then, let's see. Okay. this is your roughly, this is your T values. Okay, your V is 25. You look at 25. Okay, again, try to find where is that value of 13.86. Okay, so and then if it is within the interval, I think this one is not within an interval. Yeah? It is just bigger than a value. All right, so you read up. Just like what we did for the hypothesis test. All right, so read up. If it is an interval, read up. What is the alpha here? Let's say 0.001, and let's say here 0.0005. All right, so the p-value will have to be between this. Okay, but because this is a two-sided, so you need to multiply by 2 because the t-test is always a two-sided. So your p-value will be 2 times 0.001 and 2 times between 2 times 0.005. Okay, but I'll show you again in the next class. But in the meantime, it's just like how you do for your hypothesis test, because this is a hypothesis test. Okay, so okay, never mind. I'll show that to you in the next class. You just remind me again, yeah, how to do that. Okay, so okay, so what we'll do is, okay, now you let me know what is it that you would like to have a look. All right, and then from there, we will yeah, perhaps maybe I try to find one question on the regression, and then we can just get it done completely. Okay, all right. So I will stop here. All right. So we'll do a little bit of revision in next week's class for the chapters, yeah, on the chapter 9, 10, and 11, the regression and the ANOVA. Okay. And then we will get it done. Okay. All right. Okay. So I'll stop here. Thank you everybody for coming to class today. All right. So have a good weekend. Okay. So I'll catch up with you all next week. Okay.